Hello, this is Bruce Wallenberg again, and this is lecture 10A, where we're going to be talking about transmission system effects. It turns out that we cannot simply represent the power system as one bus with all the generators attached and all the loads attached to that bus. We have to represent the transmission system, and there are many effects that it has on the way we operate the generators. Let's take this. This is just supposed to be a map of a city. These are roads here. These dark lines are roads. Here's an airport with the runways, and we have some rivers here. We have the Blue River, and we have the. I'm sorry, that's a rail. This is a railroad. Let's put RR here. The dots are railroad tracks going around. Here is a river, and here's a river. The Red River and the Blue River here, they come together in the town, and then they come back out to the lower right corner here. And the dashed lines right here are transmission lines like this. And here's a power plant. Here's another power plant. And where the transmission lines come together, we show a substation. Now, what we don't show at the substation are all the details, but probably there are transformers coming out of the substation, or transformers in the substation with lower voltage lines coming out with more transformers, and this is going into a distribution system and so forth. The load is connected at these substations. Here's another one up here. And so we wanted you to understand here that there's a geographical aspect. These are spaced across this city and across large parts of states and the country, and the transmission systems and so forth can be mapped just as railroad tracks and roads and rivers and so forth. Now, what we're interested in the course, however, is just the electrical part of this diagram. So we've reconstructed it here, roughly the same spatial locations. Here's our power plants. Now, electrically, the power plant consists of a bus with a generator. So this is our little diagram of a generator here. Same thing here. Here's another generator. And we numbered the, we have numbers. These are just numbers, number 1 and 2. The buses for the generators, we don't try to distinguish to the buses, where this is a load bus here. Now this is a number 3. And we don't show it, but later on we're going to show loads. I like to draw loads as a little square like this coming off, and that really consists of transformers and so forth. So here's the loads that the generation is feeding. Okay, these are the loads. So here, and these obviously connecting the buses are the transmission lines. So once again, the horizontal line, this is a bus. If you're an electrical engineer, you're used to the term node. It means the same thing here. And then this is a transmission line. Okay, transmission line. I'll just abbreviate it, trans line. So there's a trans line. Let's try and make that look a little bit more like an S. Transmission line. We specifically call this a one line. Most all of our analysis is done with the one line, but we know that really the buses and the transmission lines are made up of 3. We have at a bus, we actually have 3 nodes or 3 buses for phases A, B, and C. Same thing with the lines. There will be 3 phases, but we reduce it all to a one line, and we do the analysis in what we call the per unit system, and this is where you're going to have taken or go back and get notes for a more elementary course than this one, where we show how the per unit system we can reduce the analysis. So we solve for one line, and we assume that there's a per unit impedance between the buses, and we can solve for, if we know the voltage, we can solve for the current, and then from the one line per unit system we can go back and we can calculate and decide where the three-phase quantities are. Okay, within the substation we have breakers. Now again, this is one set of breakers for one phase, and there would be 3 sets of these, one for each phase. But what we want to show here is the fact that breakers, this is the breaker right here, the B, and this is called a disconnect switch. I'll just say DS, disconnect switch. The idea now is that the breaker can operate to open large amounts of current, so that when there's a fault or when we want to energize the transmission line, we open the breaker to interrupt the current, and that would be when these are closed. And then once the breaker is open, we've interrupted the flow of current. If we need to work on the breaker, we want to isolate it from the power system. Now we open these disconnect switches, and the disconnect switch is especially designed to isolate the voltage. There's a large you'll have a breaker like this, and it's standing on some insulators, and we'll draw another insulator over here, and here's the other side of it, and it's standing on an insulator, and then there's an arm, and the arm goes up like this, and so that when it's fully open there's a large air gap. So once the disconnect switches are opened to isolate the breaker, we can take a cable, connect it to the breaker itself, and connect it down to ground. And that's the purpose of the disconnect switches, are literally to give it electrical isolation and then ground it. Once it's grounded, you can go in and work on it. It's not dangerous anymore. Nobody should be electrocuted because the thing is isolated and it's grounded. Sometimes these disconnect switches can be operated remotely. They have what they call a motor-operated disconnect. Although most of alternatively, a person will go into the substation and use a crank and insert the crank and into a gear mechanism and open them manually. Either way. So the idea here is that we have 4 lines. Now the one-line diagram of this thing would just look like this. Here's this line coming in, here's another line coming, and another one. So this is the bus. Here's the bus, and these are all lines over here, L. The breakers in this case can't do much. If there's a fault on this line, this breaker will open. If there's a fault on the bus, meaning there's literally a short circuit to ground, then you have to open all 4 breakers to isolate that. This system down here, we can sectionalize the bus. So we could, if this one were opened, then we would have the lines coming into 2 buses. So if that breaker here is open, if this is open, then this bus splits into 2, and it literally creates a second bus. So the software, especially in the operations centers, has to be able to take into account sectionalizing like this and opening of a bus. Here's another one called a main. Here's our main bus here, and a transfer bus says that well, if I have to, I've got two transmission lines coming in, and normally they're connected through the breakers. So actually, I shouldn't say we got a transmission line here, transmission line here, transmission line here. So The normal diagram of this is just simply like this. So I got three transmission lines coming into this main bus. Now, however, if we're having problems of some sort, I can open the breaker. Let's say that I'm having a problem in the substation. I can open 1, 2, or 3 of these breakers, and I can close this breaker, and that basically says that the transmission lines are now connected to this transmission line, to this transfer bus, and then I could also isolate this one back here, so I can reconnect them to this transfer bus. This one down here is called a ring bus. The interesting thing is that if I have a fault on this line here, I'd have to open 2 breakers to isolate the transmission line, but that doesn't disconnect anything else from the bus. So just opening those 2 breakers, all of the remaining transmission lines, with the exception of this one, are still connected together. That's the advantage of a ring bus. This is called a breaker and a half scheme. It's similar. We can transfer a transmission line from either to this bus or to this bus, depending on whether I have these 2 breakers closed or these 2. So I can transfer back and forth between one side and the other. Here's a similar scheme, pardon me, called the double breaker, double bus down here. Notice that it has a few less breakers. Again, for three transmission lines, it has less breakers, but it has less ability to switch back and forth. We talked about this before, that if I have a system like this with a ring bus, and I have 2 transformers down here, 2 power transmission lines coming in here, and the high voltage lines come in, the voltage is dropped, and it goes out here. If I open the 2 breakers in the middle, if I open the 2 breakers on the end, I end up with 2 separate buses like this. This transformer is connected to this line, this one's connected to this line. So I have to know now that I've split the bus. We call this roughly topology processing, meaning what's connected to what inside the substation. We propose to use a branch, bus and branch model. We talked about this before. The generator has got this circle. This is a load. Sometimes you do it like this. Other times you'll see in some of the diagrams the load looks like that. Doesn't matter. Those are both acceptable symbols. These are branches and these are buses. Now once again, these are 3-phase, but this is a 1-line diagram, and we could put, but we don't necessarily all the time put per unit. So you have to know how the per unit is a set of quantities that it's basically a scaling of everything that allows us to solve with only a single line, single bus, instead of A, B, and C. Now here are some of the applications of what we call a power flow. The dispatcher's power flow is used by personnel in the control centers, let's say transmission control centers. What are the loads throughout the system? What are voltages? What are options to unload overloaded equipment? Can I open up a line that's getting to be too heavily loaded so that the load will shift to other lines? What are options? Provide continued service as equipment fail. If I have an equipment failure, can I reconnect the system to allow the flow back into that to a load? Planning is done by engineering groups in the electric company offices. I'm going to build a new generator. What are my options for connecting it to the system? If I'm going to build a new transmission line to support more load or new generators, where do I route it, where do I connect it, what voltage do I use, things like that. DC links, we actually have what's called high voltage DC, where we convert the AC to high voltage DC, which would provide the best flows. Where should I look at a DC link? Fax devices, flexible AC transmission system devices are really power electronic devices to control the flows on the power system. Where can new demand locations, where can I build a new industrial park, for example, where I want to put many hundreds of megawatts of new load on my system? Where can it be located geographically, and I can attach transmission to it to be able to supply that new load? So that's a planning power flow for new facilities, as opposed to the dispatcher power flow, where we're working on the existing system and trying to work around problems that are confronting us right now on the system. Okay, the equations that we're going to use, we're going to start with the equations of P and Q. You know that S is is called MVA, and it's equal to P plus the electrical engineers don't use the square root of -1 symbol I, we use J, P plus JQ. And so if we look at any flow on the system, the sum of the at the buses, when you go around the bus, we're gonna do the following. We're gonna say, well, the sum of all of the S that's flowing this way, and that's flowing this way, and that's coming in from the generator and going in to the load, the sum of all of that is equal to 0. Now this is basically a result of what we electrical engineers call Kirchhoff's current law, that says that the sum of the currents flowing, let's say, into a node is 0. And it's the same, that law becomes the sum of all of the S or MVA flows. It can be translated into the sum of all the P. So the sum of all the real power going in and out of a node is 0. The sum of all the reactive power is 0. And so here we can say, well, if that's the case, then the generator at bus I minus the demand, that's this down here, minus the SIK that's down, that's this flow down here, this one, minus IJ, which is the top flow, is equal to 0. So that, and then we break that down into its real and imaginary. These are complex. So this is a complex number. Okay, this is complex. We can break that into its real part and its imaginary part, the P and the Q parts. Again, P gen minus P demand is minus PIK minus PIJ equals 0. Similarly for the Q. So these are the basis of the power flow equations, and then I can do that for, we didn't draw demand, but we can draw demand over here and demand over here. We can put it like that and just say, well, the demand plus the flow coming in equals 0, the demand plus the flow coming in equals 0 over here. You do it at every bus. So equations for P and Q in the network. Now we get into the electrical engineering part. S at any node is equal to the voltage. Now this is all these are all per unit, okay? These are all per unit, and I'm just going to say PU for per unit quantities. So S is equal to the voltage times the conjugate of the current, the conjugate of the current. So for a flow on YIJ, so this one here says that I've got a bus I over here, and I got a bus J over here, and I've got an impedance here. I'll draw a block in here, and I'll say, well, this is Y Well, then I have over here, I have a voltage, VI, which is a complex number, and I have a VJ. Well, first thing I have to do is calculate the PIJ, and this comes from using the current. You calculate the current. This really is VI magnitude at delta sub I. This is VJ at delta sub J. Sub J here. And YI is equal to a magnitude YIJ and an angle. It's a complex number, so we can make it into a polar form, and we're going to call that gamma IJ. And so if you work out the formula for the current, which is just voltage I minus voltage J times YIJ, and then break all of that into real and imaginary parts, and then multiply the conjugate of the current times the voltage, you get these two formulas, P and the formula for Q. Very nonlinear. We got products of voltage magnitudes, and we got cosines and sines in the formula like this. Okay, so we need to also define the bus types. Now, the slack generator is a generator where we say that it's a V theta bus, and that means that we know the voltage magnitude and we know the phase angle. What we don't know are the P and Q at the bus. And I often call this the reference generator. You'll hear me referring to that as the reference generator later on in the text. And it allows us to say, for example, I don't know what the flows are on the system before I start the calculation, so I don't know the total losses. So I can't tell you what the total generation, because the generation has to supply the load plus the losses. So the slack generator, it gets that name slack in its history because it picks up the slack. And so its P and Q are only known when at the end of the calculation, but its voltage is fixed. It's known. We say this is known or fixed. Okay, so these quantities are fixed. These are unknowns. Put a question mark here. These are known and unknown. You can have a demand or tie line where you can have Q fixed, and you can have Q and theta are known, and P and V. This is an unusual type of bus, but it's possible. A load bus or demand bus is one where we call it a PQ, where we know the P, we know the Q, and we say that we have to solve for these. So the unknown is solved. We solve. The generator bus, we know the P and we know the voltage magnitude. So there's P is known, V is known. What we don't know is the Q and the phase angle. So the reason the generator voltage is known is the generator internally has control system operating that controls the current in the field winding of the generator, and that controls the voltage magnitude on the generator's bus. Finally, a controlled voltage magnitude bus might have, for example, the similar G and V, but we're solving for theta and for A, and this is for a transformer. We'll show you this set of equations later, so I'll just write trans. That's for a transformer. All right, Newton's method. You should remember Newton's method that says I want to find the value of x that makes some function equal to 0. Well, I'll start out at some x0, and then I say, well, I take df dx times this delta x, and then I can solve this for delta x, okay? And you just simply say, well, how do I solve this? Well, delta x is equal to J inverse, okay, times minus f of x 0. This is times. It's not subtraction. And so all I did was manipulate this equation. I solve it for delta x, and then I say, okay, x1 is equal to x0 plus delta x. And now I go back and solve it again, only I take f of x1, and I get a new j. This is a function of x, and I get a new delta x, and then I get delta. I add that delta x to x1, I get x2, and so forth. And this is the way in which you solve the equations for the root. If you have an equation, let's say, that's going like this, and I want to know where it crosses this line here. That's the solution. Well, I start out here, and I use the slope, and then that gives me a point where it hits, and I say, well, I use the slope again, and the thing converges to that point. That's Newton's method for one variable. We can apply it equally to valued equations. So if I say I want to know the value of p, I say delta p, and I'll take the variables as theta and v, which this is, again, when you see a v, that's a magnitude. And we'll just simply write this out as dp d theta times delta theta, and the sum. Now this is summed over all of the j, all of the buses that connect to bus I, and this is the sum over all the j connected to I of dp dv times delta v, and we divide this by v. It gives a little more accurate answer to do it that way. Similarly for q. So we say that the delta p is the value that we want. This we know, the specified, and this is the most recently calculated, so that's the delta p. So this is a number, and the idea is that we get a vector of delta p and delta q, and we solve for delta. Okay, we're going to solve for delta j for every bus and vj. So we're solving for the voltage and the magnitude and phase angle everywhere on the power system. So Newton's method applied. Remember that AX equals B, then X equals A inverse B. And if the B has got all the delta P and the delta Q's in it, and it's really a vertical vector, we wrote it here with a transpose. X is all the delta phase angles and delta voltages. And then we say, okay, A has got AII, which is the dP d theta. AIJ is the dP dV. We bring this V over here. And so forth. We've got 4 different matrices like that. And then we can invert them. So then we invert A, multiply it times this. This one you build up from the difference between the known power and the calculated power. And then in the end, the X gives you the changes in phase angle, the changes in voltage. And you can apply them, and you've done one iteration. Now you go back, calculate the deltas again, calculate the new A matrices, and so forth. You iterate to the solution. The transmission line model that we use consists of a resistance and an inductance in series. Again, these are per unit quantities. here you can have this be a the YII can be a conductance and an inductor to ground. In a more popular, here's the same transmission line, but most of the time we just do this with a capacitor at each end, representing the capacitive charging of the and this just represents ground, and so this could be here, just could be a capacitor. Very seldom do you have the G to ground to cover anything, so we can write it like this. Note that the I sub ij is VI times this Y plus Yij. This is the ground, and then the VI minus VJ times the Yij across here. Technically that should be YII, not Yij. If we have a transformer, what we call an off-nominal ratio transformer, again, you need a background course for this, but when we say off, if it's a nominal ratio, the transformer doesn't show up in the model, in the per unit model, but if it's not at the nominal ratio of the per unit voltages, then we have the current like this has got this A term. Now A is a tap ratio. It can be a scalar if it's a simple voltage ratio transformer, or it can be a complex number if it's a phase angle regulating transformer. And we multiply like this, and so all we're saying is that this voltage J gets multiplied by A, and that becomes the voltage at this point. And then we calculate the S like this. Ultimately, you would learn in a basic course that it's possible to take a three-phase line. So let's say I have my three-phase line coming in out here, and I have a set of transformers that feed one three-phase AC line, and then I feed another, and the only difference here is that one of them is connected YY and the other one is connected Y delta. And then we have these 6-pulse bridges, these converters, and this is a DC circuit like this, and so the current flows in this direction and back in this direction. And at the other end, you'd have a similar converter like this with a ground in the middle, another converter like this, and it comes back out into AC again. So here's my transformers, my Y delta, and I have three-phase AC transformers out here. And this is done for several reasons. Why go to all this trouble? This is very expensive. This is very expensive. But the idea is that with a direct current transmission, we only have 2 wires. So instead of this for a transmission line where I have to have 3 insulators, this is a simple single circuit 3-phase line. I can build it like this. Well, it's only got 2 insulators and 2 conductors, so it's 2/3 as expensive for the insulators and conductors. It's only got 1 pole, and the way I built it there, and the so-called right-of-way that I need, this width of land that I need for the DC line is much less than the land width that I need for the AC line. So I don't have to buy as much land for the DC line. So it's cheaper. It is cheaper. Now it turns out that yes, it's cheaper, but in order to overcome the extra cost of the what we call the rectifier and converter stations, you usually build these for very long lines, so you have a big enough savings so that even when you add in the cost of the converters and rectifiers, it's still cheaper to build. There are other advantages to doing things with DC transmission. There's some parts of the world I could have this at 50 hertz, and I could have this at 60 hertz. So it's a way of connecting a 50 hertz and a 60 hertz system to each other through a DC transmission line. There's other things. If this line is having problems where the frequency is varying around quite a bit, over here the frequency is not affected because the frequency doesn't get transmitted across the DC link. So it's used for isolating systems where there are stability and problems. The power flow procedure. We take the input data that we get from the engineers that built the system, and we put them in the table, and we get tabular data, usually on computer files. We take the initial solution or the latest solution, we build a Jacobian matrix, and we output the Jacobian matrix. We take the initial solution, we calculate the residual mismatch, the so-called delta P, delta Q, and that gives us the net injection at all power flows. Then we compare the maximum mismatch with the acceptable tolerance, and if we decide to keep iterating, we solve that matrix equation that we had before, and we update the voltage, magnitude, and angles. So we say voltage is equal to the old voltage plus the delta V, the angle is the old angle plus the delta angle, and we go back through to again. So we're just gonna go repeat back here again, and we keep doing those steps until we've reached acceptable solution, and if everything is acceptable, we're done, and we exit like this. Here's the 6-bus sample system we use throughout the book. It has 3 generators. Here's my reference or slack bus. The generators on buses 1, 2, 3, and then we have loads on buses 4, 5, and 6. Here are the loads on the system: 100 megawatts with 15 megavars on buses 4, 5, and 6. The base kV is 230 here. The Vmax is 1.07. The min is 0.95. The bus data now says that the generator 1 will operate at 110, generator 2 and 3 at 50. Well, what is that? That's 210. Well, we're trying to supply 300, so something has got to change here. Here are the data. From 1 to 2, we have the R, the X, and the B. The B is for the capacitance at each end of the line, and it's rated for 100 MVA for that 1 to 2 line. So that's the data that we put in the computer. And here's the convergence steps and the bus summary. We start out with this much, and you notice that it goes down by almost a factor of 10, and then almost a factor of 10 again, until it gets to be very, very small. And you'll notice that instead of being 110, this one came out to 228.6, and these are each 50. And the voltage number 107 is held at its maximum bus voltage over here, and I have another printout that shows the flows. So here's the flow from bus number 1. Here's the flow to bus number 2, the flow to bus number 3, and the flows are P and Q. In this case, these two guys are at their upper limit. And last of all, limits. The limits indicator says that the P-gen on bus 2, on bus 1, the voltage is at its upper limit. Thank you very much.